This conference will now be recorded.
Hello, good afternoon, everyone. My name is Rez Mani. I'm application scientist for Allied Scientific Pro, and today's webinar topic is Near IR Spectroscopy and NIRvascan Instrument. So this webinar is being recorded, and the recording will be sent to you. My email is also at the bottom of the screen here, so feel free to send me emails after if you have any further questions or we want to follow up regarding NirvaScan. Also, we'll have a Q&A session at the end, so basically you can ask any questions, or if you need to stop me in between also, that's fine. So let's go through this webinar. This webinar, I've organized it in such a way that it will be a combination of basic theory, instrument features for different models, software, different applications, apps, and comparing the Near IR with other methods. So I'll go through difference between Near IR and mid IR, need for a portable NIR spectrometer in various applications. Then I'll explain the digital light processing technique, which is different from the traditional dispersion method for spectrometers and using the linear array detectors. Then I would introduce the NIRvascan instrument and the basically different models of NirvaScan. There is the reflectance model, the transmission model, and the fiber optic model. Then we'll go through some case studies for each model. For reflective unit, we have about 6 case studies that are listed here. For a transmission unit that is used for solutions, we have 2 case studies. And for the fiber optic unit, also we have 1 case study and 1 proposed measurement. Then we would look at the app for the NirvaScan, which is called ISC NIR. And then we look at how to transfer data from a smart device to the PC, how to record a reference. And at the very end, we would compare the Near IR method with the FTIR, which is in mid-infrared, and then we also compare Near IR with the Raman method. And we end with some conclusions. So let's move on here. So this diagram here shows the Near IR spectra. It's a small range in the electromagnetic spectrum. So basically anywhere from 780 nanometer to 2500 nanometer is the Near IR section. It is part of the greater IR spectrum. So IR consists of Near IR, mid IR, and far IR. So basically from 780 to 2500 is Near IR. From 2500 to 25,000 or 25 micron nanometers is the mid IR, and from 25 micron to 1 millimeter is far IR. So sometimes you see in the spectroscopy they use a different unit, centimeter inverse instead of nanometer. which I'll explain later how you can convert. So let's go a little bit through the history of near IR. It was discovered by William Herschel, a British astronomer in the 1800s, and the way he discovered it is because near IR is basically invisible to the eye. So the way he discovered it is he placed the thermometer in the invisible region of the dispersed spectrum next to the red, and then he saw that the thermometer temperature has increased. So he discovered that there is some kind of emission there that is causing this. And then later on, he verified that these rays will also follow the properties of waves such as diffraction, interference, refraction, and reflection. So what happens about near IR or mid IR spectroscopy is that there is an interaction of light with the material. So the IR radiation is absorbed by material only at certain wavelengths. Now, these wavelengths that are absorbed, their frequency corresponds to molecular vibrations, such as stretching, bending, wagging, and twisting. Here you see in the picture below, there is a symmetric stretching, asymmetric stretching, and two other modes. So basically, depending on how the molecule is vibrating, it will resonate with a certain wavelength that is impingent on it, and it will absorb that. So the vibrations normally lie in the mid-IR region for bonds such as CO, CH, CN, and NH. So we are looking for the fundamental vibrations between 2,500 to 25,000 nanometers. And these absorption at mid-infrared is very strong. So you have strong absorption peaks, and they are also sharp. They're well defined. The resolution is higher. So mid-IR, however, has certain disadvantages because water absorbs very strongly in mid-IR. And if your sample has water in it, the absorption by water could swamp out the absorption from other ingredients. So normally for food industry, for example, where material have water in it, mid-IR is not recommended. Mostly, mid-IR is used for petrochemicals, plastics, and polymers identification, and mostly for qualitative analysis than quantitative. So for this reason, we use the near IR region. However, in the near IR region, we are looking at overtones and not the fundamental bands. And here in this picture at the bottom shows the fundamental vibration in near 3 micron or 300 centimeter inverse. This is in the mid-IR. And then if you double this frequency, you get the first overtone. And then a second overtone, you double it again, or basically triple it, you get the second overtone. Quadruple it, you get the third overtone. And these overtones, which are about 100 times weaker in strength of the signal, lie in the near IR region. And you can also get a combination band which combines two of these, basically an overtone from one vibration with an overtone from another vibration from another bond. So the signals are more complicated, and the strength of the signal is less. However, it is possible to use an NIR for measuring samples that have water in them. Also, the measurements are faster and do not require sample preparation like the mid-IR requires. I will get into this in a little bit more detail in another slide. So next is, here is a picture of a mid-IR, and you can see all these well-defined bands for different molecules, N2O. This is from 2800 to 5200 nanometers, and the upper scale on the x-axis is in centimeter inverse. So just to convert one from the other, you can divide one by the wavelength in nanometer and multiply by 10 to the 7. So, for example, 3800 nanometer corresponds to 2600 centimeter inverse. The reason they used centimeter inverse in the past was, and still they're using it in spectroscopy, is because it's directly proportional to frequency. It's a very popular unit of usage in spectroscopy. Both nanometer and centimeter inverse are used. So we can see the high resolution strength of the signal, but here is an example of a near IR spectrum, and here is, for example, the second overtone plus the CO stretch. This is a combination band, and the bands are wider, and the strength of the signal is smaller. But it's in certain applications, it's more practical to use near IR than mid IR. So the need for a portable near IR spectrometer in various applications. Why do we need to use near IR? As I mentioned before, mid IR needs sample preparation. The equipment are more expensive. For example, you need to use certain particular windows like potassium bromide KBR window, which is expensive. Water-rich solutions swamp the other signals. And also taking the measurements in mid-IR takes longer than NIR. NIR is a fast measurement and can be used for quality control and quantitative measurements in many different industries. These are all the bands, all the bonds and the signals corresponding to them. In this chart, the first overtone region here are the NIRvascan instrument, works in 900 to 1700, so it could detect many of these CH bands and OH bands in water and NH bands for proteins and so on. So now let's go a little bit into the instrument itself. The NIRvascan instrument uses the digital light processing, which is different from the traditional method of using linear detectors. So here on the left side, you see there is these lamps, broadband light, such as a halogen tungsten lamp shining on the sample, and then it is collimated, and then basically it gets the optics projected into this diffraction grating. Diffraction grating would disperse different wavelengths, and the linear detector and in-gas array would detect each wavelength on a different pixel. So very simple in theory. However, the downside of this is that the linear arrays, in-gas arrays, are expensive. So the cost of the instrument increases because of using the linear array. So an alternative method that also helps the quality of the signal, and it increases the throughput of the light, is instead of using a linear array, something called the micromirror array is used, and this is called the digital light processing. So the dispersed light falls on this micromirror array, which has many different small mirrors, and each part of the spectrum falls on a section of these mirrors. So blue falls on this mirror, green falls on this one, and these mirrors, one after the other, turn towards the detector, which is just a single point in-gas detector. This is very much less expensive than a linear array. So one after the other, they turn, and then they turn back. Another mirror would turn towards the detector, and spectrum is constructed one piece at a time. And so this way you can accomplish the same function without using the detector array. So the DMD device, the digital micrometer device, plays an important role. So the detector, single point detector, also could be larger in diameter. It's typically about 1 millimeter here. whereas these pixels could be of the order of microns, so that would increase the throughput of the instrument. Here's the NirvaScan's optical engine, and you can see that there are two lamps. These are halogen tungsten lamps. There's a window, which is a sapphire window, and this window is placed on the powder or the, for the reflective method, you can place it on the powder or the object you want to measure, a solid object, and then there is basically a long pass filter here at 885 nanometer that cuts off all the wavelengths below 885 nanometer. There's a slit, which is 25 micron by 1.8 millimeter tall. And you can see the DMD board here, the diffraction grating, and then some focusing optics. And the single point detector would detect the radiation. So there are three models of NirvaScan, and I assume the audience have purchased different models. I know, for example, fiber optic model and reflective model, of course, is the most popular model, but for different applications, which I'll go through, different models are used. So for solids and powders, we always use the reflective model. We place the mirror, the window, sapphire window on the object, and we measure it. The lamps come on, and the instrument measures the diffuse reflectance from the object. Then for solutions, we use the transmission model. You can see there's a 1 centimeter thick cuvette that is placed inside this, and this holder, and the light comes on, goes through the solution, and is detected by the detector. So we also have the fiber optic model that does not have an internal source. So one has to use an external source and a fiber optic to use this. And that has different set of applications. I'll have some examples. I put the specification tables here at the bottom in case we need to refer to that later if there is any question. But the optical resolution is 10 nanometer, and there is 1.17 nanometer per pixel that basically is received by each pixel of that micromirror. There's something like 854 pixel on the DMD, and each one will get 1.17 nanometers. So let's look at the PC software. So the way to measure make the measurements would be either to use a PC software where you have to connect the instrument via a cable, USB cable to your PC, or if you don't want to do that, you could use the app where you have to communicate via the Bluetooth connection. So let's go through the PC software, and here are some screenshots that I have put there. So when you go to the main screen under scan settings, depending if you're using the reference, reference by the factory, if you want to do that, you have to select the built-in option here, and then this button will say scan, so you can directly go and scan your measurement. So this way, for any absorption measurement, you need to have a reference so that you compare what is reflected compared to what the original signal intensity is. So this has been already measured by the factory that built the instrument, and it is recorded there, so you could use that. However, if you want to use your own measurement, your own reference, then you have to select the new reference. Select is the new option here, and as soon as you select the new, the scan would change to scan reference. So you have to use some kind of a highly diffuse surface like Spectrolon, which I'll talk about later, to record a reference. And once you record the reference, then you can select previous, and this will change to scan. So for measuring, for using the built-in reference, there are certain settings like number of scans is 6, there's gain control, and type of scan, they're all set here, so you cannot change any of the parameters if you use the built-in reference. If you want to change these parameters, then you have to record your own reference, and the measurement also should be done in using the same parameters. Of course, the software also creates CSV files, and you can also record the measurements and later on refer to them. So here is an example of a measurement that was taken from a surface, from a paper or desk, and you can see there is the reflectance. So this is just the reflectance that has been measured from the surface, and then there's the absorbance mode, which is kind of complementary. So you see here's a dip, there's a peak, so absorption, and this is the reflected intensity, which basically to get the reflectance, you divide the reflective intensity by the reference in the factory, and then that will give you the reflectance. So how does the PC software calculate reflectance and absorbance? So measures reflected intensity from the object. Then step 2, it calculates reflectance function by using R equal to I over I0, where I0 is a reference to spectrum that has been recorded by the factory. And then it calculates absorbance by using this formula. Absorbance is equal to log of 1 over R. That will give you this plot here. For the transmission model, measures transmitted intensity through the solution and calculates transmission function by using T equal to I over I0, and then the absorbance is log of 1 over T. So this is how the simple math behind converting reflectance into absorbance, or transmission into absorbance. Now, the software also has, the PC software has the ability to overlay plots. So if you select the overlay function here, you can select several different plots and compare them together. So you want to see how things have changed. If like different samples are showing different spectra, you could do that. Unfortunately, at the moment, this doesn't have a labeling mechanism, but we are working on that to see if we can introduce a labeling and printing mechanism on this one, but it's not available at the moment. You can always print all of these in Excel. There's a CSV file, and then label them and print from there. So now let's go into some case studies that we have done to understand the performance of this instrument. So we start with the reflecting model, and the first case study is the protein and moisture content of wheat kernels. So we had a customer who was from Manitoba province in Canada and was in contact with farmers in Manitoba, and farmers need to basically quantify the protein and moisture content of their harvested wheat. And at the moment they use a very expensive instrument. They pay a lab to do this measurement for them, and so that is probably a $20,000 instrument that does this measurement. It has its own software and has a good accuracy. So the customer wanted to know if we could just make use of NirvaScan to do the same measurement to reduce the cost. So he sent us several samples. You can see 2 of these samples in here, and the moisture content and the protein content of these wheat kernels had already been measured by the expensive instrument. So we tried to do some measurements to see if we could get some useful data out of this. And you can see I placed the reflective instrument right on top of the wheat kernels, and I've made a measurement. So we did some calibration based on this, and basically the protein is in the 1500 nanometer region. That's the signal from the protein. and water is around 1450, so they're pretty close to each other. So for this reason, I'm showing here 3 samples where the water content is almost the same. So any variation you see between the samples is just due to different amount of protein. And here we already have 11.7%, 12.2, and 13.6. And you can see that there is a change in the absorption peak. So I plotted absorbance versus wavelength, and you can see there's an increase in the absorbance peak. So one can calculate with respect to a constant absorption peak, which is here at 1200, what is the difference between each peak and this peak? And I plotted it on the right plot here. Absorption peak magnitude versus the percent protein that has already been calibrated. And I came up with this linear regression line with a formula. So this way one can look at an unknown sample and find out what is the protein content by using this this formula in percent. So once you have your absorption peak, you have the y value, you could find the x by using this line formula and find the percent protein. The problem arises if the moisture contents are different, and we didn't get to testing this as far as different moisture contents are available, but the technique works when the moisture contents is similar and only protein content is changing. Another application is sweetness of fruits. Again, we had another customer who wanted to find the sweetness of fruits before picking them from the trees, particularly apples and pears. And so the glucose is mostly CH bonds. And here you see the spectra, absorption spectra for apple and pear, and several peaks that correspond to CH are observed. Around 1200 nanometers, you have peaks, and also around 1000 nanometers. And this one probably water line. So you can see a difference between different levels of sugar in this plot. And also the company that has provided the instrument has another software. It's called DeepScan, which is a cloud-based demo software, and basically the reference spectra are all stored in a cloud, and you can look at reference spectra for different fruits, and once you do a measurement with NirvaScan, it will compare the measured spectra with the reference plot, and then it will automatically tells you the sweetness level in Brix units. So here you can see I did a measurement from mango, and it came up with 16.11 Brix units, and it also labeled it as super sweet. So the Brix unit, for those of you who may not be familiar with it, is defined as 1 gram of sucrose in 100 grams of solution. So this kind of measurement is possible. The other measurement is the fat content of body, and this is actually my own hand where I'm doing a measurement, and it came up again, compared it with the reference plot, and came up with about 30% of fat, and labeled me as obese, which you could probably tell from my picture at the very beginning. I was slightly obese. So you can do this measurement from, say, your hands or feet, for example, and it will give you the degree of obesity. Another application, we had a customer who sent several fabrics from France, and these fabrics are all identified by different numbers, and they were a mixture of polyester and polypropylene, and he wanted to know if by using spectroscopy, specifically Near IR Spectroscopy, we could identify the percentage of polyester, or tell which of these have a bigger amount of polyester content as compared to the others. And the measurement also showed that particularly the 1200 nanometer band, which is a CH band, shows stronger peaks for some of these samples as compared to the others. And you could identify the polyester content. Another very interesting application is identifications of plastics for recycling. And this is a huge application which could be of much use. So the way recycling is done, most of us are not concerned with what happens to our recycling products. We just throw them in the bin and then we forget about them. But once we throw them, they are collected, they go to this recycling factory as shown in this picture, and each product has a certain label or a number or a label somehow, and products all come in a rail, and factory workers separate them and throw them in different bins. So these could be hard plastic, PVC, high density plastic, polyethylene, yes, high density polyethylene or low density polyethylene or PVC or other types, and each one has to go in a different bin. So this is done manually by the workers. But another possibility for this would be to basically use a Near IR spectroscopy to identify different spectra of the plastic, and then a camera is looking at all these pre-identified plastics, and once they come to the sorting section, there is an air nozzles that give different amounts of air or pressure of air to different types, and they go into separate bins. So this will eliminate the worker's role in here, and this could be done using spectroscopy, and basically process could be automated. So here I've done a measurement from a PVC plastic ball. It's 100% PVC plastic ball, and you can see CH bonds in the absorption plots at 1200 nanometers and around 1400 nanometers. So this is a promising application. Then we also have the automated measurements for moving surfaces. We had clients who said they were very much interested in measuring different samples that are going on a rail, an assembly line kind of, and the question was whether NirvaScan reflective model would work in a moving geometry, because normally we touch the window. Hello? Hello? Oh. Is there a question? Okay. So so the question was whether the NirvaScan could make the measurements if there are a few millimeter difference between or separation between the window and the object. So here I'm using an aluminum piece, and I've mounted the NirvaScan at maybe 2 or 3 millimeters above the surface. Let's look at this video. So you can see the light, the two spots from the two lamps are shown there. So next, there's another one from another copper-coated plate. There's another video here. You can see the two lamps. These are the spots there. So we also, I also did some measurements using the PC software, because in the PC software it's possible to do automatic measurements at certain intervals. So this encircled area here at the bottom left would allow you to choose a number of the scans you want to do and how many you want to do at what intervals. So I chose 3 seconds here because the integration time is about 2.2 Total scan time 1.4 seconds. So I chose 3 seconds so that the scans don't mix together. And I did 9 scans. So the aluminum piece here is partially covered by a tape, and here this part of it is bare. And I did exactly the same measurement, and what I saw was that the instrument could easily distinguish between the tape part and the untaped part, simply because the tape part is a good diffuse reflector. So you can see these signals that are well defined, and on the right y-axis have higher intensity. They belong to the parts that is taped. And these noisy ones belong to the parts that is just bare aluminum, because bare aluminum is not a good diffuse reflector. And if you also look at the absorption plots, these three belong to the tape section, and these the coinciding noisy absorption plots all for the bare aluminum. So basically, NirvaScan automated signal collection could distinguish between aluminum surface with tape and bare aluminum. However, we also did measurements for another client who was interested to see if there is oil on aluminum or other metals. And it turned out that the oil is so thin that the measurement did not provide a useful result for that. There was also another case where there was silicon on metal was of interest, and in certain circuit breakers, the silicon would not allow the circuit breaker to open and makes it stick. So they wanted to check to see if silicon on metal could be detected, but the thickness was so small that the results did not show a promise. But for distinguishing different reflectivity of surface in an automated mode, it's definitely possible, as is shown in here. Now let's move on to the transmission unit, which is used for solutions. So one application we had was from a customer in California who wanted to basically examine production of FDG, which stands for fluorodeoxyglucose. It's a radiopharmaceutical used in medical imaging, and it contains acetonitrile, ethanol, and cryptofix, whose formula is given here. So the idea was that he sent us some good samples and some intentionally bad samples that had the wrong mixture. And this is just to do a quality control using spectroscopy to see, without sending it to an expensive lab, they could quickly identify if some of these solutions do not have the right concentration. So the first thing we learned from this measurement, because these samples were all water-based solution, when you use a 1 centimeter thick cuvette, as shown in here in the transmission module, the absorption by water is so strong that past 1400 nanometer, you don't see any signal at all. So that was a drawback. So for this reason, another cuvette, which is shown on the side of this, was made by cutting this 1 centimeter cuvette into 2 pieces and putting them back to back. We have a glass blower that we have access to that could basically cut these, and then we put silicone on the edges. So made a 3 millimeter thick cuvette. And as soon as we poured the sample into this and made the measurement, suddenly there is another peak that is showing past 1400 nanometer that could have useful information. So for water-based solutions, you need to use a 3 millimeter thick cuvette, and 1 centimeter is not good for it. However, is my voice is not coming? Ben,
No.
are you there?
Hello?
Hello, Ben?
No, this is one of your attendees.
Are you Solomon?
I lost
Hi,
your volumes. I don't know if you're away from the microphone.
Okay, one second. Is it better now?
Yeah. No. It was good before. Don't know what happened.
All right, now is it better?
No.
Well, I'm not sure. I'm very close to the microphone as much as I can.
All
I
right,
can't.
continue then. I will dial in again and see if that was the issue because it was coming good before. Okay.
All right, so I'll try to speak louder. How's that?
That's okay. I'll put
All
it to
right,
my ears.
all right. I'll speak louder as much as I can.
Yeah, you're
So,
good. You're coming through now. Thanks.
all right, you're welcome. So you can see that the peaks appear here when we use a 3 mm cuvette, and that could contain useful results. However, when we did the analysis, the customer thought that this application did not have enough minimum detection limit for what they want to do. But it was interesting to work with this sample, and not all the examples that I show were a success, and some of them did not work, but we were just scanning through different applications to see what works and what doesn't. Most of them worked, but there were a few of them that did not work, and this is one example where we didn't have enough uh, minimum detection limit. Another application sent by a customer in the US, they were trying to find the different ingredients of a detergent that they were making, and they were pretty secretive about the ingredients. They just sent me several samples, as shown in this bottle is one of them, and asked us to do the measurement, and basically we poured it into a 1 centimeter thick cuvette, and this had no problem because this was not a water-based solution, and you already had a good signal past 1400 nanometer, and we made these plots based on measurements from all the samples, and the customer ended up buying the spectrometer. Here you could see the CH bonds here that are very prominent. Now let's move on to the fiber optic unit. So the difference between the fiber optic unit and other units is that this unit does not have an internal source. So it is useful if you are using an external source. And the first test that I did was to measure the spectrum of quartz halogen tungsten lamp by Newport. This is a collimated lamp, and basically I used the fiber optic, which was in the Viz Near IR, so it ranges from 400 nanometers to 2200, and measured this spectrum by pointing the fiber optics at this white paper. And this is very typical of the QTH lamp. So this is quite useful for applications, especially maybe field applications where you have an external source and you're looking at a fluorescent light or something like that. Another possibility for this, or very important application for the fiber optic model, is when you want to do measurements in the flow mode or flow system. And here you can see a flow cell where you have a source and you have a sink, and the liquid flows through this flow cell. And if you couple a lamp through one input, then you can take the output and go to the spectrometer and measure the concentration or the spectrum in a flow geometry. This can be coupled to a 1.5 millimeter PTFE tubing with 0.5 millimeter inner diameter, and the fiber optic also has a range of 400 to 2200. Okay, so these are a few applications. Now let's look at the app. I have recorded a video for both the Android and also the iOS app, but I'm only showing the iOS app video. If some of you want the Android video, I can send it to you. You can email me, I'll email it to you. So this is an iPhone here, and this is the NirvaScan. So let's look at this video for a few minutes. Read how to use NIR and NirvaScan spectrometer with the ISC NIR scan app on an Apple device. So this is an iPhone, so I'll turn on the NirvaScan. The lights come on here, the green light and the blue light shows there. And then I would tap on the icon, and I get to the main screen, which has a big lens in the center. I go to the gear box at the bottom right, and then you see select device to connect. I tap on go, and then you see while I tapped on go, the device appears here. So if I tap on it, I go back there, and then I go to the main. So I go and tap on the big lens, and here it says looking for NIR MRR1. So now it's going to download some data, some calibration files, and a few calibration files are downloaded, and then it gives you the message tap button to scan. So once you get the tap button to scan, I'm going to start the scan here, and then we'll see the light is coming out of the window. So light, you can see, is coming out of the window, and the scan is done. And then it says receiving data. So you see intensity data, absorbance, and reflectance. That's about it. Thank you. Okay, so this was the app. We also have another video for the Android, as I said. Now, what about transferring? Okay, what range is being scanned? Okay, Solomon, the range is 900 to 1700. That's the range of the instrument. 900 nanometers to 17. Yes. Yes. So how do we transfer data from the iOS app to the PC? So for the iOS app, you have to use the iTunes and connect the iOS smart device to the PC using the USB cable. Open the iTunes, and then you will see there is basically this symbol here of a phone here. So once you click on that, then you get this window, and then you go to file sharing. There's a folder called ISC and IR scan, and all your measurements are already listed there. Here I have only one measurement. So you can transfer these files to your computer this way. There's no need for emailing or anything. It's just directly you can do it. Once you use the Android, you can just use the file transfer option of your smartphone, and then that would ISC and IR scan appears as a folder there, and then all your files are there. All right, so if you remember in one of the earlier slides, I said if you want to change any of the parameters like averaging or gain or the scan mode, you have to record your own reference. So how do you record your own reference? You have to have a highly diffused surface like in SpectroLon. And this is an example of that from a company, StellarNet. Has 97% diffuse reflectivity. So you would go to new first, and then it says scan reference, place the spectrometer on this surface, make a measurement, and then you go to the previous, and then you use that reference that you recorded for your new scan. So I highly recommend this model, 97 diffuse. I've even compared the reflection from this with the factory model, and they're very much the same. So you can use this. Now I would like to compare Near IR to FTIR, which is in the mid-infrared. The pros and cons. There are different spectroscopic techniques. So why are we using Near IR, and how is it different from FTIR? Some of you may be familiar with the FTIR, Fourier Transform Infrared Spectroscopy. So Near IR is a dispersive method, uses a broadband source, diffraction grating, separates the broadband into different wavelengths, and then material is absorbs depending on its molecular bending and stretching properties, certain wavelengths. And the diffuse reflective model that I showed you is an example of this dispersive method because it measures the reflectance, and then from there it calculates the absorbance. However, in FTIR, it's a different method. It's an interferometric method. The full broadband beam of the source shines on the input of the interferometer, A sample is placed in one arm of the interferometer. So example is given here. You can see the sample is placed. This is the interferometer. One mirror is stationary, the other is moving, and basically the sample, the light goes through the sample, and once the mirror is moved, interferogram is recorded, and the Fourier transform of this interferogram will give you the spectra. So it's very different. You would do the measurement with and without the sample, and then by using these two spectra, you can calculate the absorption. So you can see how diffuse reflectance, where this scattering, there is the reflectance from the surface and maybe beneath the surface a little bit is causing the signal to come up. And this method, which is interferometric, is very different. So this usually used in the mid IR, so a fundamental vibration. Near IR uses overtones. There's also the method of translative reflectance in near IR, where you have in food material where you have seeds, the near IR source goes through the material and is reflected and transmitted, and finally is coming out of the CD sample, is focused into the detector. So the two methods are different. So what is the comparison of near IR and FTIR? Pros and cons of FTIR. For pros, it has a high throughput because in near IR, if you remember, I showed you there was this entrance slit on the instrument. So the throughput is limited by the entrance slit. But in the FTIR, the full throughput is used. Now, FTIR uses fundamental bands, whereas NIR uses overtones and combination bands that are weaker, narrow bands for FTIR, high resolution, lower resolution for the NIR. And what are the cons of FTIR? It cannot measure watery material because water signals swamp all the useful spectral information. And then if the materials is heterogeneous, it cannot penetrate beyond the surface. The near IR turns out could penetrate more in the surface, beneath the surface. So once you do FTIR, you only get information about the surface in the reflective mode. So it also needs to do sample preparation. Normally, samples are mixed with liquid paraffin, or it has to be grinded by potassium bromide to get better uniformity. But the near IR method does not require sample preparation. The hardware is more expensive. The detectors and the windows are very specialized in mid IR. For near IR, inexpensive detectors, a smaller size of the sensor, and they're less expensive. So this is some advantage of near IR. You also have the technique of FTNIR, where they use the NIR source instead of a mid IR source, and use the Fourier transform technique. But that also had some issues because there's a moving mirror, so the size of the instrument is larger, and the cost is also more. So in our case, we have the micro mirror, and it is less likely to break than a moving mirror in an FTNIR. Another technique is called the Raman spectroscopy. So comparing near IR and Raman spectroscopy, they are different because Raman is not based on absorption, but is based on a scattering. So here is a diagram that shows there are three types of scattering. What you call a Rayleigh scattering is when the scattered light has the same frequency as the incident light. And then you have Stokes and anti-Stokes, where the scattered light has more or less frequency than the incident light. So basically, each one of these is used for one application. If the molecules does not have a center of symmetry, like it's made of two different atoms, like a CH bond or OH or CO bond, then the technique of choice is NIR. But if the molecule is symmetric, like a CC bond or CC double bond, then the Raman, it works better in that case. Here is a diagram for Raman. He uses a laser source, and the notch filter blocks the laser source. Basically, is a sample chamber, and it uses sophisticated optics, spectrometers, micrometers to detect the very weak Raman signal. Whereas in Near IR, the measurement is much faster and is much stronger. However, if you have a sample that is symmetric, like a CC bond, then Raman will be the technique of choice. So you can see example of this CC double bond, CC triple bond. So what are the cons of a Raman method? Data is not normalized and hence a relative measurement because we don't know what's the references exactly, whereas in the Near IR we know. It's a more expensive instrument because of the presence of laser. It's a weak effect, and you need to block the laser source to observe the signal. And fluorescence is also a big issue because there are a lot of problems with fluorescence when you use a Raman, because a fluorescent signal could swamp the Raman signal. So this is almost the last slide. I'm going to finish very soon. So the question is that the spectrum that you measure when you are using the Near IR method is more complex than the mid IR, because it could be a combination band you're looking at. It could be a harmonic you could look at. So if you have many different material in your sample, they could basically give you confusing results. So one has to use some statistical methods, and chemometrics as a technique where you could use principal component analysis and partial least square analysis. These are statistical techniques that could basically identify what are the components of your material or your sample, and would allow you to identify different components and quantify it. There's a software, it's called Minitab, which is very common, that could be used to do this statistical analysis. If you buy a $20,000 instrument, NIR instrument, it usually comes with its own software, and it does the analysis for you. It has a capability of doing the statistical analysis. But if you buy the NirvaScan spectrometer, then you have to use an external software like Minitab to do your statistical analysis and find different ingredients. So in conclusions, what are the conclusions for this talk? The NirvaScan reflective model showed promising results in applications related to food industry, textile industry, health monitoring, plastics for recycling, and moving geometry measurement. NirvaScan transmission model showed promising results for solution quantification of some liquid-based solutions, such as liquid detergents. We also find that 1 centimeter thick cuvette for the transmission model swamps the signal past 1400 nanometer due to water absorption. A 3 millimeter cuvette is recommended. NirvaScan fiber optic model successfully measured the spectrum of quartz, halogen, tungsten lamp, and it was also proposed that you could use it for a flow measurement. And finally, NIR technique is a fast, non-destructive technique which requires no sample preparation, can be used in identifying, quantifying, and sorting many materials in different industries. It can be used in process monitoring, and in particularly useful to find the moisture content in different materials. So with this, I would thank you for listening to this presentation, and if you have any questions, please feel free to ask. Are there any questions? You can also type here if you like. What difference would you see doing DR for DR? What is DR? Sorry.
Sorry, diffuse reflectance.
Oh, diffuse reflectance, right. What difference would you see doing diffuse reflectance for FTIR versus NIR? Yeah, the difference was what I mentioned, that FTIR that uses like mid-infrared does not penetrate too much into the bulk of the material, but near IR penetrates more. So if you have a heterogeneous material, the FTIR only would give you information about the very top of the surface. And also the other difference is that FTIR is more expensive. The cost is a big issue. FTIR systems are very expensive as compared to even a handheld FTIR is more bulky and is more expensive and uses more specialized parts like KBR windows and Meerkat detectors and things like that.
What would be the particle size when you use a diffuse reflectance with your instrument?
What is the particle size?
Yeah, what would be the typical particle size? You know, in terms of microns, less than 1 millimeter, less than 2 millimeters.
Well, it depends on how you grind it. Like, let me show you an example here. For example, here you can see here I've used the seed, right? These are seeds that are for wheat kernels, and these are few millimeters. Okay, so you can still get useful information here. But you can also make powder. I've made measurements from sugar, very fine material, very fine micron size. So as long as it is a few millimeters, it's fine. You can do measurements. You can also do it from solid surfaces. Like I could do measurement from a paper, for example, or a desk. Or I also showed you like you can also do here. I showed you one where you could measure from aluminum, the tape on an aluminum. You get decent signals. It doesn't necessarily have to be a powder. It could be a surface, but a diffuse surface. Like if it is a very shiny surface, for example, if it is just a reflective aluminum, it will not give you good results. It has to be more diffuse.
Okay.
Yes.
Well, do you have any examples of an organic material which would be coated and an inorganic material? I'm thinking more of things like application here would be in asphalt, coated and rocks. Do you have any application like that?
Yes, for rocks, actually, I do have. I have looked at some mineral rocks. So there are some rocks that they're fluorescent. So you can make a measurement. But I know your application is asphalt. I've been told about this. So may I ask, is this like a solid? You're going to put it on solid asphalt, or you're just looking at the ingredients, the powder form?
Think of it as a composite. It's a composite of mostly 90% rocks, and the rest is this thing that it's coated, right? So,
right, but I'm asking, is it in a powder form? Is it in a powder form, or is it solid?
It can be made in it because there's a gradation of sizes, and of course you can reduce it down to 2 millimeters. Yeah, in a powder form, because you wouldn't want to just put in a half-inch rock. You see what I'm saying?
Right.
It wouldn't work.
Yes, so it should be not a problem then. If there is IR signature, near IR signature, it should be able to measure it. Well, I'm not particularly sure about asphalt because I've never done a measurement from asphalt, but if there is a NIR signature, the instrument could definitely measure it in a powder form.
Yeah, it could have polymers in there, like a styrene butadiene polymer in the asphalt with the matrix, low level. So that would be, you did talk about some percent fiber, I think was plastics or different things. I don't know what the lowest level in terms of percentage that you measured and those composites that you showed.
Yeah, we didn't. The only quantitative measurement that we made was from the wheat kernels. So we normally leave the quantification part to the customer to do.
Okay.
They have to do their calibration themselves. So I could not tell you what is the minimum detection limit in this case.
Right.
But one possibility is, I don't know if you're interested in this or not, but one possibility is that you could send us a sample of your powdered asphalt, and I could do a quick measurement and basically look at the spectrum. I can send you the spectrum, and then you can look at that.
You talk about non-destructive testing. So my question in terms of this particular application, can I take the device? I cannot, I mean, in order for me to get, let's say I have a surface of the pavement, I normally can take a portable device and point on the surface and get a signal.
Yeah.
Can I take your device and take it to the pavement and do that rather than I can drill, but that it becomes now destructive. You see what I'm saying?
Yes, so yes, absolutely.
Non-destructive, I want to take the instrument and point it to the surface, right?
Yes, you can do that, definitely, because as I showed you here, this is the app that does that, right?
Okay.
So here you don't have connection to the computer. It's just you turn on the Bluetooth, and you get the results with your smartphone in an Android or an iPhone.
Yeah.
That you could make a measurement without any connection to any computer.
Oh, so that's the spectrometer I'm looking at there?
Yes. This is a spectrometer.
Interesting.
Yes. And it just communicates via Bluetooth. You could use the app to communicate via Bluetooth. So you can take it outside. Pardon?
So you can take this and just point to the surface of any surface, right?
Yeah. Well, you should actually place it on the surface.
No, yeah. When I say that, I mean like if I have a piece of paper, just put it on the paper and just scan it. Is that what you're saying?
Yes, that's right.
Yeah, it has to touch it. I understand that. Yeah. It's not remote sensing. It's a direct contact. I understand that. Okay.
That's right. But then there's the issue is that I would say that if your surface is very rough, like you have to be careful not to scratch the window of the instrument. You see, like you have to place it gently. You have to place it gently. Even on a rough surface, you could do the measurement because I did it from rocks, from mineral rocks. I was very careful not to scratch the window. I placed it very gently.
What is the window material?
It's sapphire.
Okay, all right. Yeah, I understand that. It goes, you just carefully place it on the surface, right? Yeah, okay.
Yeah, yes.
Okay. How many scans, can you control the number of scans related to, say, the resolutions, the number of scans?
You can, let me just go back to the PC software.
I thought you said the scans that you said were fixed, 6 scans, and I didn't understand that pretty well. How many scans can you do? Can you change that? If I want to do 50 scans per second, I don't know how your parameters are.
Yes, you can definitely do that. Here, let me just go back to that slide that shows that. Let me just go back to automated measurement. Yeah, in the automated measurement. So if you look at this plot over here, right? It's not very clear right now, but I just try to increase the size a little bit maybe. Yes. So you see over here, you could put it on an auto, and you could just say, here I've chosen 9 scans at 3-second interval. So the instrument would automatically measure it 9 times, one after the other at 3-second interval. But if you want to increase the integration time, you can only do it to increase the averaging. The parameter that you could choose here, number of scans to average, you can change this. Right now it's set to 6, but you could do 10 or 12, whatever. But you have to do a calibration, because my point was that if you change this parameter, then you have to record a new reference. Sorry, not calibration, a new reference. And for that you need the Spectrolon. So you need to buy the Spectrolon, you set that to 12 measurements or 12 averages, and then you do a reference, and then you also do the same thing with your your sample.
So let me understand it. So I wouldn't want to use your internal reference. You saying?
Yes. If you want to use the internal reference, then you can't change the parameter of like number.
Okay, got it. Okay, got it.
If you want to change that, then you have to record a new reference.
Oh, I got it. Okay. All right.
Okay. Any other questions? You're welcome. Any other questions? All right. Okay, so if there's not, thank you again for listening to the presentation, and feel free to email me, rmani@alliedscientificpro.com, or you could email Mr. Ben, and he will forward your question to me. Have a nice afternoon, and hopefully we'll be in touch soon again. Bye now.
Thank you.
Thanks.
Bye.